constraint-based pattern mining. So with data mining, it'd be nice to be able to try to automatically find all the patterns in a data set. But that can be really unrealistic. There's just too many patterns, it's not focused. It could take too long, not very efficient for our processes. So data mining should really be an interactive process. And this is useful in most real-world cases. Otherwise, we ended up with too many patterns and not particularly interesting. And so some controls based on specific application and our domain knowledge or some prior knowledge can be helpful. So with constraint-based mining, we add user flexibility and system optimization to enable us do more efficient mining and providing constraints on what to be mined, what we're looking for. Different types of constraints. For knowledge type constraint, we care about frequent patterns. Don't care about classification, or you don't want to classify association, clustering, etc. The second one is data constraint. So using SQL-like queries, we can find product pairs sold together in stores in Chicago this year using CU Campus instead of not national. Right, so we can do that constraint on the data that we're looking for. Dimension level constraint. This would be an example, a street address versus the neighborhood versus the city. And so what level in that concept hierarchy do you want to use? Use all the dimensions or a subset, and what level? And rule or pattern constraint. So here we have meta rules or rule templates. Use a specific template to capture the kind of rules you're interested in. So for example, the number of attributes, attribute values, maximum number of predicates, or minimum. You can look for small sales, like prices less than $10, or triggers on big sales, like sum is greater than $200. So instead of finding association rules of customer traits and what they buy, we want to find customer traits that buy Alexa, for example. For interestingness constraint, we look at the strong rules. So for example, minimum support greater than or equal to 3%, a minimum confidence of 60%, and correlation as well. All right, so for this meta rule guided mining, we look at the left-hand side and the right-hand side of our association rule. X can be a transaction, or it could represent a customer, depending on the context. So the method to find these meta rules, we're finding frequent item set predicates based on this minimum support threshold. And the idea would be to push these constants deeply when possible into the mining process. So we use confidence, correlation, and other measures when possible. And so here, this is the idea of determining these meta rules as opposed to just being given these rules. So constraint properties, we have a bunch. We'll look at the anti-monotonic, monotonic, succinct, convertible, and inconvertible. So certain constraint properties can help with pruning our pattern space. So with the anti-monotonicity, we're working with a set. So this is for item sets for these. And if our item set, say call it S, violates the constraint, then so does all of its supersets. So S is a subset of the superset. So if our S item set is already violating the constraint, then any superset would also be in violation. So for example, let's say we were doing a priori, and the sum of all prices in an item set should not exceed 100. So if you already have a subset of items in the basket that exceed 100, there's no superset that can fix that, because you're violating this constraint, and all subsets are guaranteed to also violate it. So that's the idea behind the anti-monotonicity. So in a priori, for example, we can reduce the number of candidate item sets examined based on these types of constraints. So if we look at this example rule constraint, these we've got three of them coming up. are they anti-monotonic? So the first one is the sum of a subset, the price, is less than or equal to 100. All right, so what we want to do is look at the sum of any subset once you hit 100. So once you violate this, once we get up to 105, anything else that's a superset that contains the subset will also violate this. So yes, this is anti-monotonic. All right, now if we take that same constraint and then flip the sign here so that it's the sum of our subset is greater than 100. All right, so would this be anti-monotonic? So if this item set violates it, so let's say we have a basket of items, milk and bread, and it's only coming up to $6. So the price of this subset is only $6, so it violates as greater than or equal to 100. All right, the thing is though, we can keep adding to it, or if we've only checked out those 2 items and there's still 20 more to go, we might end up meeting this constraint. And so this would not be anti-monotonic because we have to keep going through the rest of the set and find the full superset that may satisfy this constraint. If we look at the range, this has the range of the subset prices is less than or equal to 50. All right, because the term is less than here, less than or equal to, if our subset already violates this, so the range is maybe it goes from 1 to 100, the prices in our basket. Any superset, any more items we add to our basket here, we're still going to violate this. All right, so this third one also is anti-monotonic. Okay, so then we have monotonicity. This is similar, just check how it's different from the anti-monotonic that we just talked about. So for monotonicity, if an item set, so again we have this set S, if it satisfies the constraint, then so does any of its supersets. All right, so let's look at an example. So sum of the prices is greater than 100. So if we have a basket and we've got cookies and ice cream and meat and everything, and it comes out to $105 already, and we're still not done checking or looking at anything that might include additional items. If we're already satisfying this, then the superset, any items we add will still satisfy this because we're not adding, there's no items that have negative values. So this would be an example of being a monotonic constraint. If the minimum price of our subset is less than or equal to 100, so that is satisfied. We have some item, we bought a pack of gum and it's like $2. So this is satisfied. Well, anything we add to our set, our item set, we're still gonna meet this constraint, all right? Because that minimum, it's just the minimum price. So we only need one item to meet this requirement. So this is also monotonic. If we look at the range of our item set prices, is it greater than or equal to 15? So if we already satisfy that, if an item set is already greater, the range is greater than or equal to 15, then so does every superset that contains this set. Okay, so then succinctness, if we look at succinctness, we're looking at enumerating only those sets that are guaranteed to satisfy the constraint. So if we have, for example, the minimum of the subset price is less than or equal to V. All right, so is that succinct? Can we enumerate all and only those sets that are guaranteed to satisfy that constraint? So we're looking for the minimum price, and then yes, that would be a succinct rule, constraint rule. If we're looking at the sum of the prices of the subset being greater than something, is that succinct? So it's not succinct because we don't have a way to enumerate only a subset of items that would satisfy to guarantee this. So with the succinctness, we have this pre-counting prunable. So succinct because we can generate all item sets that satisfy the constraint before we do our counting. So it helps us in our pruning process. Convertible constraints. So this is looking at a combined version. If we take these tough constraints convert them into anti-monotonic or monotonic. And the way we're going to look at doing that is by properly ordering the items. So something like an easy one was the minimum, right? The minimum price in the basket. That's quite easy. But when we have something more difficult like the average of the profit, of the sales profit in the set, what we can do is convert this to make this easier to work with by ordering our items. So our average, we're looking for it to be above, greater than or equal to 25. So this will get violated if we end up below this. So without order, and we're calculating the average of our transactions, and we don't have order to it, then you could have $1 plus 250, and the average, when you're calculating the average as you look at each item, it can fluctuate a lot. So you cannot really figure out the average until you look at all the items in that subset. So if we order the items, as I go through, if the average goes below this 25, then I know that the rest of the items in my basket or my item set are less, then I know the rest, it's going to violate this, and it becomes anti-monotonic. Right, so that's helping us be more efficient in our process here. Okay, so if we take the profit, we order them in descending order. So here we have our items and what the profit is. And so we take these and put them in the correct order. A is 40, which is the highest value. E is the lowest value at negative 30. So we've got 40 through the negative 30. And we start to calculate the average. So if we're looking at a subset of the full set, right, so here we have AFB, AFG actually, so 40, 30, and 20, and you calculate the average, and we get 30. So that meets this constraint. The average is greater than or equal to 25. And then we add the 10, and we still get greater than or equal to 25. And then when we continue on and we get to the 0 here, and once we've added these values and calculated the average of these, we hit 20. That's below the 25. And if I continue processing, there's nothing to fix this to get the average back up above or equal to 25. So we know that any further processing, we know that this superset here is going to violate this constraint. So it becomes anti-monotonic. Now, strongly convertible, if we look at this, the average, it could be convertible to anti-monotonic if we sort it in descending order. It's also convertible to monotonic with respect to ascending order. So in that case, we say that this particular constraint is strongly convertible. Okay, so here's another example. We have a constraint, the average of x is greater than or equal to 25. We have a minimum support of 2. So we list all the items in our transaction. This is the same type of example, just walking through it again. Descending order, so we start with A is the 40, 30, 20, 10, so we have them listed out. This is our subset, our set here are in order. Our constraint C, this is our constraint up here, is convertible anti-monotonic with respect to R, as long as it's in descending value order. So now what we can do is we scan the transaction database once. We can remove any infrequent items. So if we have a minimum support of 2, if you look through here, H is the one that's only in here once. So we can drop item H, not have to work with that. And then the item sets, A and F are good, and we can meet this C constraint. So this is kind of the process that we would go through. So if our subset violates C, then so does any superset based on the anti-monotonic. So when we look at these variety of classifications for our constraints, we can see how they would overlap with each other in this particular diagram. This is kind of a high-level benefit of Anti-monatomic, if the constraint C is violated, its further mining can be terminated. For monotonic, if C is satisfied, our constraint is satisfied, then there's no need to check C again. That would be like the minimum value. Succinct, constraint must be satisfied, so one can start with the data set satisfying C. Convertible, C is not monotonic or anti-monotonic, but it can be converted to be one of those for the transaction as long as it's properly ordered. Okay, so let's look at one more example. Suppose our association mining query, we have find the patterns or rules about the sales of which cheap items, so we're defining cheap items to be the sum of the prices is less than $10, may promote or appear in the same transaction the sales of expensive items. And so we're defining expensive items when the minimum price is $50, shown in the sales in Denver in 2016. All right, so that would be what we're trying to mine. That's our query. And so what we want to look for is, what are the constraints within this text? And then we want to determine, are they monotonic or anti-monotonic, as well as are they succinct? So the first one, if we look, the sum of prices is less than $10. So we can write out the constraint that the sum of our subset I of the price is less than $10. All right, so then we ask, is it monotonic or anti-monotonic? So remember, anti-monotonic would be if an item set violates the constraint, then so does all its supersets. So once that sum gets violated, you cannot unviolate that. So this would be our anti-monotonic. And then is it succinct? Well, no, because a superset could violate this constraint. So the next constraint in our text, the minimum price is $50. So we can write that out. The min of our subset price here is greater than or equal to $50, the minimum. Okay, so is that monotonic or anti-monotonic? So remember that monotonic, if an item set S satisfies the constraint, so does any of its supersets. And so if we find a minimum value, we're just looking for one that satisfies that constraint. So that would make that a monotonic. And is it succinct? Well, because this is minimum, once we find a subset that meets this constraint, then we're guaranteed that the subset, well, any superset's going to also hold true because we've already met this constraint. So it is succinct. All right, so now let's look at what else we have in here for constraints. We also have in here that the city is Denver. And for that, this is not talking about the item sets, right? So this is just simply our pruning of the data. So we don't talk about monotonic or anti-monotonic. This is simply constraint on the data set. And same with the year being 2016. So that we're just essentially doing our data pruning based on these constraints then.